Wrapping up our chapter on limits and derivatives, this section 2.8 is really going to just piggyback on the last section. You can see a lot of similarities to what we did in 2.7 and finding the derivative. We're going to change some variables to help us going forward as we go into chapter 3. So in 2.7, we said that the derivative function at a point A could be modeled by this equation. This was my favorite equation that I used. I like this one better than the f of x minus f of a over x minus a. But what we're going to do is we're going to change our point of view and let a vary. Okay, so we're not going to be really interested in what's doing at a number, but what it's doing in general over the function. And so I'm going to replace a with an x, and that's going to be the equation that we use going forward. So now it's just going to look like this. Limit as h approaches 0 of f of x plus h minus f of x all over h. Now the graph of f is given in figure 1. What I want to do is I want to use it to sketch the graph of the derivative. And I'm just going to throw this right here on the same graph. Okay? So I'll be using a red line for my derivative. So this blue line is f. What would the graph of f prime of x look like? Well, the first thing I notice is that I'm looking at my horizontal tangent lines. Right here, my graph levels off, meaning that at that red line right there, my slope is equal to 0. If my slope is equal to 0 right there, pretty much what I'm doing is I'm keeping all the same x values, but I'm changing all my y values to be the slope of this blue line. So everywhere I have a horizontal tangent line, I know that is going to be a 0 of my derivative. Got another one here. Okay. And so my graph's going to wiggle around the axis a little bit. I'm more interested in where it's increasing and decreasing versus where it is the upper and lower values of it. So first up, I'm looking at all of these points now that are to the left of this 0. If I look to the left of it, I had a very steep line right here, a very steep negative slope. And my slope becomes more and more, less negative, closer to 0 as I got closer. And so I'm just going to bring my line up from here. Now, in between these 2 points, I'm going to switch colors and kind of follow what I'm doing down here. I see that my slope's always positive. It gets pretty close to 1 right there, but then it levels back off. And it comes back down. Now, my slope's going to be negative for a long time right here. Let me switch colors again. My slope's going to be negative for a really long time before it levels back off. And I'm not really worried about just how long it's negative, but it's just going to be negative until it reaches back to this 0. And so it's negative, so this blue line right here is below my x-axis. And finally, my line ends with always being positive. Ooh, it gets pretty steep there. Look at the slope of this little line right here. And so my line just kind of comes up, and that would be good enough. Let me retrace my derivative line here. This is a struggle. It's kind of abstract to think about it this way, but that would be my answer. So I've assigned a couple of those in your practice problems. Play with them. It might not look exactly like the back of the book, but it might be close enough to suffice. So for a lot of our remaining examples, I'm just going to be looking at finding a formula for f prime. And it's going to look very similar to what we did back in the last section. So I'll go ahead and work this one with you. I might turn you loose on some. So it says that in order to find f prime of x, remember I'm saying f prime of x, it's going to be x cubed. Oops, I'm sorry, I got that written down. Let me go ahead and write it as a limit. As h approaches 0 of f of x plus h minus f of x all over h. So replacing what I know now, I've got to plug in x plus h in for both of these x's. So that's going to be x plus h cubed minus x plus h. Again, then in step 2, I've got to subtract right here. I'm subtracting off my f of x. I like this one a lot better because you don't have to worry about plugging in a's. You get to just stick with one variable on this, that's the x. And I guess the h as well. Okay, so I've got to expand this binomial right here. Okay, unfortunately, it's not x cubed plus h cubed. If you need to write it out 3 times and FOIL it, please do so. I'm going to be using a binomial expansion theorem on it, which states that my coefficients are going to be 1, 3, 3, and 1. I start with an x cubed, and then I go to an x squared, x to the first, and then x to the 0, which would just be 1. And I just work my way in reverse and do h cubed, h squared, h to the first, and then no h at all. Put my little plus signs in there. So I was able to expand it in one step. If I remember, I'll post a video on how I expanded that so quickly. Now, good things should happen here. Everything that doesn't have an h should cancel. Sure enough, it does. And everything that is left that does have an h, I can factor that out to the front, or I'm going to start using a shortcut on it. This h down here on bottom is just a common denominator that's going to go with every term that's left in the numerator. So I'm just going to divide every term in the numerator by h. Okay. So that's going to leave me with a plus 3xh right there, plus an h squared, and then a minus 1. That's going to cut out some work for me. And now if h is going to 0, that means that term's going to disappear, that term's going to disappear, and finally, I'm left with my derivative. My derivative of this function at any point x that I would want to plug in would be 3x squared minus 1. I got 2 more similar examples. Let's see which one I want you to work. I think I'm going to let you play with this one. I might get you started on it. Ooh, I'm going to leave that right there. Might get you started on it, but I'm going to let you play with this one. Shorten my video a little bit and get you a little bit more active on it. So this is what I'm still using. Okay, I'm still using my my derivative formula that has h in it. Okay, so plugging in x plus h, that's going to be the limit as h approaches 0. Square root of x plus h minus 1 minus exactly what you see all over h. Okay. I'm going to give you a hint. Multiply by the times you get on this. So multiply by the times you get at the top. I'm going to let you take this one so you can get some practice in on it. Once you're done, hit play again, and then we'll check the answers. One over 2 square roots of x minus 1. Careful on that. Leave that plus sign in there. Remember, we're not simplifying the bottom of these limits. This is a little bit longer. We'll work this one together. So we got a quotient on it. That's going to pose some problems because my function is a quotient, my derivative is a quotient, so I end up with some extra stuff floating around in there. Okay. So go ahead and plug this in together. I'll talk you through this one. So again, plugging in x plus h, I don't think that's going to be tough. Don't do this. Don't be that guy that wants to do this. Okay, be overprotective with those parentheses. Okay, anytime you plug something in, use parentheses. I don't even need them on bottom. I'm going to put them there just so I can remember that they're supposed to be there. Ooh, it's going to be a dandy here. I might be writing too big. I'll have to come back and erase part of it. Now, a couple different things I can do on this. I can probably work this by eliminating that denominator. But I'm going to go ahead and start. Yeah, I'm going to go ahead and eliminate the denominator. So that's going to have me multiplying by my denominators. Okay, so you can think least common denominator. Don't stress about finding a least common denominator. I've got several students doing that this year. I just want to use the common denominator. I have two denominators that are in the way, right here and right here. To clear it out from denominators, I'm going to go ahead and just multiply everything by those denominators. I'm going to lose my parentheses on that one because I really didn't need it to begin with. Okay, so that's supposed to clean it up. That'll make it so I don't have this complex fraction, this fraction inside of another fraction. Okay, so whenever I multiply this whole numerator by this term right here, my 2 plus x plus h's will cancel. Alright, so cancel and cancel. And I'm going to go ahead and distribute that negative on top. 1 minus x minus h will be left to multiply 2 plus x over here. There's one distribution. Move this out of the way. So he comes back in place, bringing my minus sign down. Let me give you a reference right here. And now I got to multiply the 2 plus x. Or actually, it's going to be this whole thing again. But the 2 plus x's this time will leave the equation. And so that leaves me with 1 minus x. Again, I'm going to put that in parentheses because I'm going to have to multiply that 1 minus x times this whole common denominator on the side. Yeah, that was a lot. Hey, luckily, when it comes to simplifying the bottom, we're still just saying no. Not doing it. So I've got some distribution on top right here. Got to multiply some stuff through. So I'm going to take the 1 times the 2, 1 times the x, and negative 2x, and negative x squared, and then minus xh. Doesn't look like enough terms. What happened? 2x, negative 2x, negative x squared. The negative 2h didn't get any love. Negative 2h some love there. Alright, I think all the terms are accounted for. Not in the right order, but close enough. Alright, same thing over here. I'm going to distribute this 1 all the way through, and the negative x all the way through. So the 1 is going to be easy. In the negative x, I'm just going to change the sign and give each term an x. I should get it. I told you I was going to run out of room on this one. Okay. Well, hoping some stuff cancels here. We got 2 minus 2. Alright, it's gone. X minus x. That's gone. Negative 2x minus negative 2x. That's gone. Negative x squared minus negative x squared. Alright. Well, I'm going to move this up here to the top. I got the limit as h approaches 0. Maybe I can squeeze it all right here in this little area. So I got a negative xh and minus a negative xh. That left as well, didn't it? Negative xh minus, yeah. Still going. I was just used to leaving everything that has an h in there. So that leaves me with a negative 2h minus h. That doesn't go away. I've still got the negative 3h. It's good. I'll still be able to do some canceling here. Okay, so my h's are going to cancel. And I'm going to go ahead and just combine steps right here. And then once those h's cancel, I have negative 3 over what's left. And so that h will go to 0. And I do believe I'm going to be left with my derivative. Negative 3 over, well, I have 2 plus x times 2 plus x in the denominator. That would just be 2 plus x squared. And that is my derivative. This would be a good spot to take a break if you needed to. I'm going to keep going with this video, but that would be a good day right there if you're wanting to split this up over a couple of days or a couple sessions. There are some other notations that some mathematicians use to denote derivatives. We've got our buddy f prime of x. That's what you've seen me use a lot. We can also just call it y prime. That would denote that I'm taking a derivative. We have dy over dx. The d is standing for delta. Remember, this was just an average rate of change, but we just shrunk it down to where it's an instantaneous rate of change. So we have delta y over delta x. We simply call it dy over dx. We got df over dx. I don't use that much, but we're differentiating the function with respect to x. You can pull the d over dx out in front. I do this a lot. Of the function. That still means I'm taking the derivative of f of x. I really don't use this one, but just in case you see it down the road, capital D of f of x. It's the derivative of f of x again. And the derivative with respect to x of f of x. All of those are fair game notation. Like I said, these 1, 2, 3, 4, 5, you'll see me using throughout the rest of the year. Okay, let's talk about a function being differentiable. A function is going to be differentiable at a if f prime of a exists. Well, there's some things that make f prime of a not exist, but it can be differentiable at a, or it can be differentiable on an open interval from a to b, or on an infinite interval from a to infinity, negative infinity to a, or even negative infinity to positive infinity. But in order to be differentiable on an interval, it has to be differentiable at every single number on the interval. Not just the endpoints, but every single number. So let's go back to our absolute value function. Okay? Remember, our absolute value function can be defined as a piecewise function. We said that it was, I need to write it like that. We said it took on x, if x is greater than, up to or equal to 0, negative x, if x is less than 0. Okay, so I'm going to take the idea that x is greater than 0 first. And since h is so small, h is going to be approaching 0, let's go ahead and assume that if I add h to it, it's also still going to be greater than 0. So if x is greater than 0, that means I'm pulling my equation off the top piece. Okay? And again, h is so small. If x plus h is greater than 0, I'm still pulling my equation off the top piece. So that's going to help me do my derivative now. Okay? So my derivative is going to be the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x all over h. Well, from what I just stated up here, that x plus h is just going to take, the absolute value of x plus h is just going to take on this value, x plus h, because we're doing the top piece right now. Same thing with the absolute value of x. It's just going to take on x, since x is positive, all over h. My x's cancel. It leaves me with a positive h over a positive h, which would just be 1. Okay? So what we can conclude is f is going to be differentiable at any x greater than 0, is what I've shown. Well, what happens whenever x is less than 0? So I'll be using the bottom piece on this. If x is less than 0, that means anytime I have the absolute value of x, it's got to take on a negative x. Okay. And then x plus h is also going to be less than 0 because, again, this h right here is so small. H is approaching 0. It's so small that whenever I do the absolute value of x plus h in this case, it's going to equal the opposite of x plus h as well. So using the same math that I did earlier, using the same equation, whenever I take the limit as h approaches 0 of this function, this time it is going to give me some negatives in here. Let's see what that does to it. So negative x plus h minus x. Actually, that'd be minus negative x, wouldn't it? And it's all over h. Alright, I'm going to get rid of some of these parentheses so you can see what's going to cancel a little bit better. But everything the same is going to cancel. I got negative x minus h plus h all over h. So yeah, once again, negative x and positive x cancel. And I'm left with negative h over positive h, which is just going to be a negative 1. And so what this shows is that f is differentiable at any x less than 0 as well. Alright, the bald math teacher's been rambling for a while. What's all this mean? Where's he getting with this? Hold on just a second. Let me go back. Alright. So, the only thing that we haven't checked yet, we've done x is less than 0. We've done x is greater than 0, x is less than 0. Let's see what's happening possibly at 0. So at 0, there's not really any reason to plug in. We know it's going to follow this piece. It can actually follow any piece because negative 0 is still going to be 0. But I'm going to find out what's happening at 0. Okay, so I'm going to take out my variable x because I know what my variable is this time. It's going to be 0. So if I still do the same limit as h approaches 0, I change some stuff. X is going to be 0. F minus 0 over h. That's going to be, let's see, absolute value of 0 plus h minus the absolute value of 0. Sorry, that looks like LOL. That's all I can see whenever I write that. So I'm wanting to see what's happening with this limit. Okay, so I think something weird's going to happen with it. So I'm going to break this down. I'm going to be taking the limit as h approaches 0 from the right. And let's see what that does first. So limit as h approaches 0 from the right. So if I'm approaching 0 from the right, 0 from the right, this guy right here is going to stay positive. I'm actually just going to be left with the absolute value of h over h. If I'm approaching 0 from the right, h is going to stay positive. I get h over h, which is going to be 1. Okay, let's approach 0 from the left. LOL again. So the limit as h approaches 0 from the left would still be absolute value of h over h. But this time, if I'm approaching 0 from the left, it falls down into this bottom piece right here. So that's actually going to give me negative h over h. Those will cancel and give me negative 1. I have two limits approaching 0 from opposite ends that do not exist. And since my limits are my derivative, then what I can conclude is f prime of 0 does not exist. And there's a reason it doesn't exist. I'm going to show you graphically why it doesn't exist here in just a minute. However, Theorem 4 states that if f is differentiable at a, it has to be continuous at a. So on that last example, we're not running into really a problem with continuity, because on the absolute value of x, that thing's continuous everywhere. But if it is differentiable at a, then f has to be continuous at a. So what might be causing a function to fail to be differentiable? Well, it falls into one of three categories. Okay, how can it fail to be differentiable? First off, if f has a sharp corner. Okay, I'm going to call this a kink. That's what it looks like to me. It's like I got a kink in the water hose. Okay, if I have a kink in my water hose, I'm just going to graph the absolute value function because that has a kink in it. If I have a sharp corner, this point right down here at 0 made it so the absolute value of x was not differentiable there. Okay, second off, just what the last theorem said. If f is not continuous at a, then it's not going to be differentiable at a. Okay, in order to be differentiable, it has to be continuous. Okay, so what would a discontinuity look like? Hopefully we know this. Suppose I come up to here, and then Mario has to jump down. Okay, so right here at a, that would be a discontinuity. Right here at a, this sharp kink would be a discontinuity. And the last thing you have to watch out for is if f has a vertical tangent line at a. F has a vertical tangent line at a. So suppose I'm moseying along and all of a sudden, whoosh, it just comes straight down. So right here at a, this would be a no-go. And why is that? Well, the reason that is because the slope of my tangent line does not exist. I'm dividing by 0 right there. So that would be a no-go for it to be differentiable there. Alright, great song right here. I'm running a little bit short on time because I've got to get somewhere in about 7 minutes. So I'm going to skip the Creed video, but man, favorite song right here whenever I was a senior 20 years ago. Hard to believe it's been that long. Maybe if you're in class, we'll just take a moment and just reflect on this song. Okay. But higher derivatives. That's right. You can take the derivative of a derivative. Well, I didn't erase. Isn't that crazy? Taking a derivative of a derivative? Who in the world would want to do that? A lot of people do. And it's actually very helpful, especially if we get into the world of physics. So if I'm looking to take the derivative of a derivative, I simply call it a second derivative. A second derivative. Okay. And so Leibniz also came out with some notation on this. And so the second derivative, he wrote it. He just put a 2 in here. That gets really confusing to me. So if I'm taking the derivative of a function y with respect to x again, he said you can write it like this. I think Newton did a much better job nailing it as far as what the notation should be like, and makes the notation a little bit easier. Okay, so let's actually try this. I want to find and interpret the second derivative. Now, we already took the first derivative of this, so I'm going to save myself a little bit of time. If you go back and look at, I think it was the first example we did today. It was right after the graphing, so maybe the second example that we did today. We found that the derivative of this was 3x squared minus 1. So, what I can do now is I can find a second derivative. A second derivative on this is simply just going to be doing the exact same process, but using this as my f of x. So what does that look like? It's going to be f prime x plus h minus f prime of x all over h. I'll work horizontally this time. So I'm going to just plug in x plus h into here. Okay. And then I'm going to subtract off my f prime. Again, look at my use of parentheses on there. I'm going to make sure everything cancels, because everything should cancel again if I work this right. And let's not switch colors yet. So I got to expand this out. So square the first term, take the product of the two and double it, square the last term, distribute the negative all over h. Got one more step here, and then I should be able to do a little bit of magic on it. Make it so it cleans up. Alright, let's see what cleaned up there. 3x squared, negative 3x squared, it's gone. What happened? Forgot a 1, didn't I? Alright, let's go back and bring it in. This 1 got to come down. So it would come down right here. There we go. So that's the good news with this. If you can see when you messed up, because if everything that doesn't have an h doesn't cancel, then you can go back and retrace your steps and find out where you went wrong on it. So now I'm left with 6x plus 3h whenever I divide everything by h. H is going to 0, so I end up with a second derivative of 6x. So what is this telling me? What is f double prime telling me? It's actually telling me the rate of change of f prime. It's telling me how fast f prime is changing, or it's telling me the slope of the curve of my derivative function. Now, in physics, this is pretty nice because it gets used a lot in physics. So if I'm looking at finding the instantaneous rate of change of velocity with respect to time, that's my definition of acceleration. And so the acceleration of the function is simply going to be the derivative of the velocity. So in other words, in order to find acceleration, all I have to do is take the derivative of velocity. And we've done that. Well, remember that the derivative of velocity was simply the derivative of the position. Okay? And so if I just take a second derivative of my position function, it takes me straight to the acceleration. And we'll be doing that some in the homework. I am going to skip this Leibniz notation because we don't need it. Alright, so let's go back to our example. Same one we've been doing. We just found that the first derivative was 3x squared minus 1. And the second derivative of x was simply equal to 6x. Right. I want you to go ahead and work out the third and the fourth derivative of this function. Okay, and I'll work it out as well, and then we'll see where we're at after you hit play. So go ahead and hit pause. So for my triple derivative, my third derivative, I got 6. But you know what? I probably could have told you that even with this, because I know if I graph this line, 6x, that's just a straight line that has a slope of 6. No matter where I'm at on this line, my slope is equal to 6, which is the derivative. So using that same reasoning over here, if I was to graph the line y equals 6, 1, 2, 3, 4, 5, 6, it's just a horizontal line. And the slope anywhere on a horizontal line has to be 0. So the fourth derivative of this function has to be 0. Something weird's going on here. We're going to look further into that when it comes to chapter 3. But for now, here are some problems for you to do. Make sure if you have questions,